Hello there, and welcome to The Sleepy Scientist, where curiosity gets comfy and bedtime stories come with a touch of stardust and science. I'm glad you're here. Tonight, we're going to take a gentle journey through the night sky, tracing the soft shimmer of stars and answering a question as old as stargazing itself. Why do stars twinkle? Now, I do hope this video helps you unwind and drift gently off to sleep. But fair warning, it might get just interesting enough to keep your brain quietly buzzing. If that happens, well, at least you'll be lying awake, learning something fascinating. Not a bad trade, really. Before we begin, I'd love it if you could tap that like button. It helps more sleepy minds find their way here, and maybe even subscribe if you haven't already. I'd also be delighted to know where in the world you're watching from and what time it is there. Feel free to share in the comments below. Are you just climbing into bed, or has the night already wrapped itself around your home like a soft, quiet blanket? Wherever you are and whatever time it may be, let's get cozy, relax, and gaze up together. The stars have been waiting. Let's begin with a question you've probably asked yourself at least once. While staring up at the night sky, why do stars twinkle? You've seen it, a star flickering gently in the black canvas above, winking and shimmering like it knows a secret. It's beautiful, mysterious, and oddly soothing. But why do stars do that? What's happening way up there, or more accurately down here, that makes them sparkle like cosmic glitter? Well, the first thing to know, a simple and elegant truth, is that stars don't actually twinkle. Not really. If you were to float above Earth's atmosphere, out in the quiet vastness of space, stars would appear as steady points of light. No flickering, no shimmering, just calm, unblinking dots of distant fire. So if stars themselves are stable beacons, the twinkling must be happening somewhere between them and us. And it is. The culprit is the thin, invisible blanket of gases wrapped around our planet Earth's atmosphere. You see, starlight travels a very long way. We're talking trillions of miles. It crosses the cold, silent void of space without so much as a wobble. But then, in the final tiny stretch of its journey, just the last 60 miles or so, it hits our atmosphere, and suddenly, things get a little chaotic. The Earth's atmosphere is not a still uniform shell. It's more like a shifting, swirling ocean of air, constantly moving and changing. It's full of different temperature layers, varying densities, pockets of moisture, and gusts of wind. Think of it as a giant, transparent lava lamp, beautiful, but not exactly stable. As the starlight passes through this ever-moving air, it gets bent. This bending of light is called refraction. You've seen this before, like when a straw looks like it's bending in a glass of water. That same principle applies here, except with a billion times more complexity. Now imagine starlight passing through layer after layer of air, each with a slightly different temperature and density. The light bends slightly in one direction, then another. It jiggles, it wobbles. It doesn't travel in a straight line anymore. And by the time it reaches your eyes, it appears to be dancing ever so slightly, twinkling. This effect has a name: stellar scintillation. It's a beautiful phrase, isn't it? Like something from a poem. But it's pure science, the name for the shimmering of stars caused by the atmospheric turbulence between them and us. Interestingly, not all stars twinkle the same way. Some seem to pulse brightly, others shimmer softly, and a few don't seem to twinkle much at all. That's partly due to their position in the sky. Stars closer to the horizon twinkle more dramatically than those overhead. Why? Because when you're looking near the horizon, starlight has to pass through more atmosphere, thicker layers of air, more turbulence, more distortion. It's like trying to spot something across a steaming hot road versus looking straight up into a clear sky. The stars directly above you have the most direct path to your eyes. They don't have to wrestle with nearly as much air, so they twinkle less. Still, even at their steadiest, there's usually a gentle shimmer to them, a subtle flicker like a candle far across the room. Now here's a quirky detail that is easy to check yourself. Go outside on a clear night and look for a bright, steady light that isn't flickering. Chances are you've found a planet. Planets, being much closer to Earth, appear as tiny disks in the sky, not just points. And because they're disks, the light from their wider shape is less affected by atmospheric distortion, and so they shine with a calm, unwavering glow. Of course, this wasn't always understood. For most of human history, people saw twinkling stars as something magical, even alive. This is a common historical fact, woven into countless cultures. Some believed they were ancestors watching from above their eyes, glinting in approval or judgment. Others imagined they were lanterns lit by gods trembling in the night wind. The word twinkle itself feels whimsical, doesn't it? It's a soft, lyrical word. It dances off the tongue. That's probably why it found its way into lullabies and nursery rhymes, Twinkle, Twinkle, Little Star being the most famous. A simple question from a child's song that even adults find strangely profound. But beneath that childlike wonder is a world of physics and atmospheric science quietly humming away every night. It's the same starlight that guided sailors across oceans, inspired poets and astronomers, and helped early civilizations mark the passage of time. And all the while, it twinkled more because of Earth than the stars themselves. The twinkle you see is a very local and very human phenomenon. It exists only from our point of view, shaped by the air we breathe and the world we inhabit. It's a reminder that even as we gaze out into the cosmos, our experience of the universe is filtered through the lens of home. This brings us to a quiet and subtle academic debate that still lingers in the halls of modern science. While the physics of refraction is well understood, the precise dynamics of atmospheric turbulence, the movement of air in different temperature and pressure layers, is incredibly complex. Scientists are still debating the exact models of atmospheric fluctuation, which is critical for designing the adaptive optic systems that can eliminate twinkling for ground-based telescopes. The atmosphere is a living, breathing, chaotic system, and while we understand the broad strokes, the fine details are still a rich area of research. But for tonight, you don't need to worry about the fine details. You can simply let your thoughts float up there with the stars for a while. They'll shimmer and flicker for you, just as they've done for every soul who ever looked up and wondered. The stars, those vast ancient fires, are steady and patient, and the twinkle, that little dance of light, is just Earth's way of saying hello. It's a final, beautiful flourish added to a message that's traveled across unimaginable distances. The air around you, which feels so still in this quiet moment, is a subtle artist painting the stars with emotion and life. Every gentle flicker you see is made possible by a breeze. You can't even feel a momentary shift in temperature or pressure. It's as if the sky is breathing in and out, each breath sculpting the starlight just enough to make it sparkle. And all of this is happening for you in this moment, in this peaceful place. You are at the very heart of the show. Let your own breathing become slow and deep. Feel the air as it enters and leaves your lungs. Remember that this same air is what gives the stars their magic. You are not a spectator to the universe. You are a participant. And the quiet rhythmic dance of the stars is a reflection of the quiet rhythmic dance of life itself. A life that is beautifully, imperfectly, and always in motion. Now that we've let our thoughts settle on the dance of starlight, let's take a slow, peaceful dive into the very place where that dance begins and ends for us, Earth's atmosphere. It's a place we often take for granted. We breathe it, we feel the wind from it, we watch the clouds drift through it. But it is anything but a simple transparent shell. It's a vast, layered ocean of air. And to understand the secrets of the twinkle, we have to travel through its different currents and depths. The atmosphere is made up of several distinct layers like a giant cosmic cake. From the surface of the Earth upward, these layers are the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. Each one plays a role in shaping the journey of starlight, but the one that makes the biggest difference, the one responsible for almost all of the twinkling, is the troposphere. The troposphere is the layer of atmosphere closest to the Earth. It stretches from the ground up to about 6 to 10 miles high, depending on where you are. If you've ever flown in an airplane, you've spent time in the upper parts of the troposphere, sipping tomato juice and hoping your luggage didn't end up in a different time zone. This layer contains most of the air we breathe and nearly all of the weather we experience: clouds, winds, rain, snow turbulence, and those slightly judgmental seagulls at the beach. The troposphere is a planetary mixing bowl. It's full of temperature differences, moving air currents, and little whirlpools of heat and moisture. It's the layer that is most chaotic, most dynamic, and most filled with life. And when light from a star passes through this churning soup of air, it bends. Sometimes it bends just a little, sometimes a lot, but either way it bends. And that bending is what makes the star appear to jiggle or flicker. Now let's talk about refraction, but gently. Refraction is what happens when light changes speed as it moves from one substance to another, say from the vacuum of space into the dense air of Earth. Light travels fastest in a vacuum, slower in air, and even slower in water or glass. That change in speed causes the light to bend. You've seen this before, probably without realizing it. If you've ever dipped a spoon into a glass of water and noticed it looked like it snapped in half at the surface, you've witnessed refraction. Or maybe you've stared at the wavy lines rising from hot pavement on a summer day. Same thing. That shimmer, that ripple, is light being bent by the heat-distorted air. In the atmosphere, refraction happens all the time, but the atmosphere isn't a single sheet of uniform air. It's made of countless little patches, each with its own temperature pressure or heat and moisture content. These differences create pockets where the air is slightly more or less dense, and starlight gets bent every time it passes through one. Think of it like this. Imagine you're looking at the stars through a calm swimming pool. If the water's still, you see the stars clearly. But now imagine someone doing cannonballs nearby. Every splash, every ripple, every shift in the water changes the way the starlight moves. The stars begin to shimmer, stretch, and wiggle. The atmosphere does the same, only with less splashing and fewer inflatable flamingos. This is a quirky detail you might find interesting. The degree of twinkling or stellar scintillation is often so strong that professional astronomers use it as a way to measure the seeing conditions of the night sky. On nights with a lot of twinkling, they say the seeing is bad meaning. The atmosphere is very turbulent and making it difficult to get a clear image with a telescope. On a calm night with very little twinkle, the seeing is said to be good. It's a beautifully simple metric, a kind of natural weather report written in the stars themselves. So while you might find a lot of twinkle magical, an astronomer is probably hoping for a night that is as boring and steady as possible. Now, while the troposphere does most of the heavy lifting, when it comes to twinkling, the higher layers contribute too, just in a quieter way. The stratosphere, which sits just above the troposphere, is calmer and less turbulent, but it still has temperature gradients that can affect the path of starlight. The mesosphere above that, where meteors burn up, adds a final sprinkle of refraction, especially for stars near the horizon. The higher up you go, the thinner and colder the air becomes. But even these faint, icy layers can wiggle the light just enough to add to the twinkling effect. It's a bit like adding extra layers of frosted glass over a lamp. Each one adds a new flicker, a new shimmer, until the final glow reaches your eye with that familiar, comforting sparkle. This brings us to a common historical fact about early astronomy. Long before anyone understood the layers of the atmosphere or the science of refraction, skywatchers knew that the atmosphere got in the way. Ancient astronomers, from the Babylonians to the Greeks, understood that the location of stars and planets was sometimes slightly shifted by atmospheric effects. They also noticed that the light from stars near the horizon, having to travel through a thicker part of the atmosphere, was often distorted and less clear. They didn't know why, but they knew it was a factor. This simple observation led them to develop clever techniques to correct their measurements, often by taking them when the stars were directly overhead, or from high-altitude locations where the air was clearer. The struggle against the atmosphere's distortion is a fight that has been ongoing for thousands of years. The way the atmosphere bends light doesn't just cause twinkling, it can also shift the apparent position of stars slightly. This is an academic debate that has been settled for a long time, but it's still important for astronomers. The amount of refraction depends on the temperature, pressure, and wavelength of light. Scientists are still debating the exact models of atmospheric fluctuation, which is critical for designing the adaptive optic systems that can eliminate twinkling for ground-based telescopes. The atmosphere is a living, breathing, chaotic system, and while we understand the broad strokes, the fine details are still a rich area of research. But before we get lost in the details of telescopes and space observatories, let's return to the poetic side of this dance. Because in a way, Earth's atmosphere turns every clear night into a kind of living light show. Without it, stars would shine with perfect steadiness. Beautiful, yes, but perhaps lacking that little touch of magic. There's something quite charming about the fact that the stars twinkle not because of what they are, but because of where we are. It's a very human phenomenon. Twinkling exists only from our point of view, shaped by the air we breathe and the world we inhabit. It's a reminder that even as we gaze out into the cosmos, our experience of the universe is filtered through the lens of home. The atmosphere, which feels so still in this quiet moment, is a subtle artist, painting the stars with emotion and life. Every gentle flicker you see is made possible by a breeze you can't even feel a momentary shift in temperature or pressure. It's as if the sky is breathing in and out each breath, sculpting the starlight just enough to make it sparkle. And all of this is happening for you in this moment, in this peaceful place. You are at the very heart of the show. Let your own breathing become slow and deep. Feel the air as it enters and leaves your lungs. Remember that this same air is what gives the stars their magic. You are not a spectator to the universe. You are a participant. And the quiet rhythmic dance of the stars is a reflection of the quiet rhythmic dance of life itself. A life that is beautifully, imperfectly, and always in motion. Now that we understand the thin atmospheric sea that gives stars their shimmer, let's step into a related mystery that has probably crossed your mind when you look up at the night sky. If stars twinkle because of the air between us and them, why do planets shine with a calm, unwavering light? It's one of the easiest tests in backyard astronomy, a way to tell the difference between a distant sun and a celestial neighbor. The soft flickering of a star like a candle in a breeze is something you'll recognize instantly. But those bright, steady points of light, the ones that seem to hang in the sky with a quiet certainty, those are often planets. So why the difference? What's happening that makes a planet glow with a serene certainty while a star dances for our amusement? It all comes down to size, or more accurately, apparent size. Stars are incredibly far away, even the closest one beyond our sun. Because of this vast distance, stars appear to us as infinitesimally small pinpricks of light. They are not disks. They are not dots. They are just single shimmering points. And that's important, because when a point of light travels through Earth's turbulent atmosphere, it's highly vulnerable to all the atmospheric refraction we've been talking about. Each little patch of moving air can bend that tiny light path just enough to make it appear to jump ever so slightly in the sky. To your eyes, that movement appears as a flicker or a flash, a twinkle as the light shifts, position or intensity. But planets, while still incredibly far away, are much, much closer. On a cosmic scale, they are practically our neighbors. Venus, for example, can come as close as 25 million miles from Earth. That's a long way, of course, but it's a tiny fraction of the distance to the nearest star. Because planets are so much closer, they don't appear to us as pinpoints. They may still look like tiny dots to the naked eye, but under a telescope, or even just from the way their light behaves, they're actually small disks of light. And here's the key: when light comes from a disk, instead of a point, it's much more stable, even when the atmosphere distorts the light coming from a planet. The effect is averaged out across its wider shape. One part of the disk might get bent slightly in one direction, while another part is bent in a different direction. The overall effect is a kind of visual averaging, and the flickering tends to cancel itself out. The result is a calm, steady glow. Imagine this. You're looking through a wavy piece of glass at a tiny sharp point of light like a laser dot. The dot will dance and shift dramatically as the glass distorts the image. But now imagine looking at a larger glowing light bulb through that same glass. The light bulb still gets distorted, but the overall image remains much steadier. That's the difference between how we see stars and how we see planets. And here's a quirky detail you can use to impress your friends and family. Once you know this trick, you can go outside on a clear night and put it to the test. Find the brightest star in the sky. Is it flickering, flashing, and dancing? Then you've found a star. But if it's glowing with a serene, unwavering light, chances are you found a planet. Venus is a classic example, often called the evening star or morning star. It's the third brightest object in our sky after the sun and moon. But unlike real stars, it shines with a smooth, creamy glow. Jupiter and Saturn, too, are often visible to the naked eye and stand out for their steady, calm presence. They don't twinkle. They assert themselves quietly. Now there are exceptions to the rule. Planets can twinkle, but it's rare, and usually only happens when they're very low on the horizon. This is because when a celestial object is near the horizon, its light has to travel through a much thicker and more turbulent slice of atmosphere to reach your eyes. The more atmosphere, the more distortion, and so even a disc-shaped object like a planet can start to flicker a little. But in most cases, the difference is obvious. Planets sit steady while stars sparkle. This isn't just a fun trick for backyard stargazers. This simple observation has been a common historical fact that has helped astronomers for centuries. Long before telescopes existed, early sky watchers learned to distinguish stars from planets just by paying attention to how they behaved. In ancient times, planets were known as wandering stars because unlike the fixed background of the stars, they moved across the sky on their own slow paths, and crucially, they didn't twinkle like the others. Even the ancient Greeks noticed this. The philosopher Ptolemy, living in the 2nd century CE, noted that stars had a flickering nature, while planets did not. This simple distinction was a key piece of the puzzle that helped astronomers map the heavens, track celestial movements, and ultimately understand our place in the solar system. The difference in twinkling also leads to a more philosophical academic debate. While the science of why they twinkle is well understood, there is a subtle debate about the psychological experience. Psychologists and philosophers still debate why our brains find the dynamic, unpredictable twinkle of a star so much more compelling or magical while feeling the stability of planets as ordinary. Perhaps our minds are drawn to the dynamic and unpredictable, or maybe the subtle flicker of a star feels more alive. The answer, of course, is not a scientific one, but a deeply personal one. But the story doesn't end there. You see, twinkling, or the lack thereof, is more than just a visual oddity. It's a reminder that everything we see in the sky is shaped by both what it is and how we're looking at it. The atmosphere, the distance, the angle, the apparent size, all these factors come together to create what we experience as the night sky. The sky isn't a static painting. It's alive, moving, changing, revealing just a little more to anyone willing to stop and look. Planets with their calm glow might not dazzle in quite the same way as their twinkling cousins, but they're no less magical. In fact, once you start noticing them, it's hard not to feel a quiet sort of connection. That point of light isn't a distant star in another galaxy. It's a world, a place, a real physical body orbiting our sun, lit not from within, but from the reflection of our shared star's light. Some of those planets have moons. Some have storms. Some have rings. And some just maybe have mysteries we haven't even imagined yet. So while the stars may twinkle and steal your attention with their glittering charm, don't overlook the planets. their calm, steady presence is a different kind of wonder. One that whispers instead of sings. And as you lie back and look up, letting your eyes wander across that cosmic sea, try to spot the ones that hold still. The ones that don't flicker, but just are. They're not stars, they're neighbors. And in the grand silence of the night, they're keeping you company. Long before we had telescopes, satellites, and space probes, long before anyone knew what a photon was, or what the atmosphere even did, humans were watching the stars. Night after night, they gazed up at those twinkling lights and wondered what they were, why they moved, and what their strange, shimmering dance could possibly mean. And when we don't yet have science to explain something we do what humans do best, we tell stories. Every culture on Earth has looked to the stars and spun tales around them. This is a common historical fact, from the oldest oral traditions to the most complex ancient mythologies. The sky was a canvas for our collective imagination. Some imagined them as gods, others as spirits, ancestors, animals, or omens. The way stars twinkled, flickering, changing color, vanishing and reappearing, only added to their mystery. To the people of ancient times, this wasn't just the result of warm air and light refraction. It was magic or divine will or maybe a message from beyond. In ancient Greece, for example, stars were often associated with the gods of Mount Olympus. The shimmering of the stars was said to be the gods playing in the heavens, or the light of divine chariots racing across the sky. One particularly bright star might be considered a hero placed in the sky by Zeus himself. The flickering. Perhaps that was the hero winking at his descendants. The Greeks also told the tale of Orion the hunter, who was placed in the stars after his death. When his constellation twinkled brightly in the winter sky, it was said to be him hunting once more, his bow drawn in the shimmering darkness. Meanwhile, in Aboriginal Australian mythology, some of the oldest continuous cultural traditions on the planet twinkling stars were often interpreted as signs from ancestral spirits. Different communities had different stories. Some believed that the shimmering stars were campfires of ancestors burning far off in the sky. Others saw twinkling as a way for the spirits to communicate with the living, offering guidance, reassurance, or sometimes warnings. One story from the Yirrkala people of northern Australia describes how the stars are part of the dreamtime, the foundational mythological past when ancestral beings created the world. When stars twinkle rapidly, it's seen as the spirits becoming more active, watching over the people on Earth and keeping an eye on their actions. In ancient Japan, the story of Orihime and Hikoboshi explains two bright stars, Vega and Altair, that shine across the Milky Way. According to legend, the two were lovers separated by a heavenly river, only allowed to meet once a year. On that night, if the stars twinkled brightly, it was believed the lovers were especially happy to see each other. If clouds blocked the sky, they cried, and their tears became the rain. Even the Norse, with their mythology rich in giants, gods, and cosmic wolves, had tales of the stars. They believed the sky was a great dome made of the skull of a giant, and the stars were holes through which the light of the celestial fires shone, the flickering of stars. Perhaps those fires were burning and crackling softly behind the curtain of night. In Central and South America, the Maya and Inca peoples were keen observers of the stars. They built temples aligned with celestial events, tracked planetary movements, and used the twinkling of certain stars to predict weather patterns. In some traditions, a rapidly flickering star was thought to foretell a coming storm or drought. The sky wasn't just a canvas of stories. It was a living calendar, a warning system, a spiritual map. Of course, not all myths were friendly. In some cultures, a twinkling star might be an ill omen. It could be the eye of a watchful spirit, or a warning of war or death. The unpredictable nature of twinkling, how a star might suddenly flare or fade, was unsettling as much as it was beautiful. In parts of West Africa, some communities believed that stars were the spirits of unborn children or the recently departed. Their flickering was interpreted as a kind of communication, a whisper from another realm. The brighter the twinkle, the stronger the spirit. It was a comforting thought that the dead were not gone, just shining above, still keeping watch. And we can't forget the famous North Star Polaris. It doesn't twinkle nearly as much as other stars, especially when it's high in the sky. This gave it a reputation for steadiness that made it a powerful symbol across many cultures. To ancient navigators, it was a guide. To spiritual leaders, it was a sign of constancy in a changing world. The fact that it didn't twinkle much was part of its mystique. It was like the one star that kept its cool while all the others danced. A quirky detail that ties into this storytelling is the etymology of the word twinkle itself. It's a word that sounds like what it describes, a kind of onomatopoeia for light. The word traces back to Old English meaning to gleam or sparkle. And its sound-based nature shows that even in language we were trying to capture the feeling of the phenomenon, not just the science. The word is soft lyrical, and it dances off the tongue. It's no wonder it found its way into our lullabies. Even in more recent times, twinkling stars have continued to inspire art, music, and poetry. From the classic lullaby, Twinkle, Twinkle, Little Star, to Van Gogh's swirling masterpiece, The Starry Night, we've never stopped being enchanted by those flickering lights above us. And that's what makes twinkling so special. It's not just a side effect of atmosphere. It's a bridge between science and story, between the observable and the imagined. Even now, when we know exactly why stars twinkle, there's still something magical about it. Knowing the physics doesn't take away the poetry. It adds to it. It tells us that our ancestors weren't wrong to see mystery in the stars. They were just looking with a different kind of eye, one that blended observation with wonder facts, with feeling. And in a way, we still do the same. We now understand that a star's flicker is caused by shifting air and bending light. But that doesn't stop us from making a wish when we see one sparkle. Our understanding has deepened, but the feeling of awe has stayed the same. This is a subtle but important point of academic debate. Psychologists and philosophers still debate whether scientific understanding diminishes a person's sense of wonder, or if it actually adds to the world's beauty and complexity. Some argue that scientific knowledge demystifies the world, while others believe it reveals an even deeper, more profound sense of wonder. The twinkling star is a perfect example of this. Knowing the scientific explanation for its dance doesn't make it less beautiful. It makes its dance even more incredible, a message from an ancient sun delivered to our eyes by the very air we breathe. So the next time you find yourself gazing up at the stars and watching them twinkle, try this: imagine the stories they've told. Think of all the people who have looked up before you thousands of years ago on different continents with different languages and beliefs and seen the same flicker. Maybe they saw a god, maybe a spirit, maybe a sign of love or loss or hope. You might see something different, or maybe just maybe you'll see the same thing. They did: a little light, a little motion, a little mystery, and a whole lot of sky. For as long as people have been watching the stars, there have been those determined to understand them, not just admire them or tell stories about them, but measure them, track them, predict them, and maybe, just maybe, unravel the deeper truths hidden in their shimmer. Enter the ancient astronomers. Long before computers, telescopes, or satellite imagery, there were sky watchers. Diligent observers who spent night after night mapping the heavens by eye alone. These early scientists noticed things most people missed: how the stars moved when they rose and set, and yes, how they twinkled. They knew that starlight was not a still and steady glow, but a living, shifting phenomenon. And they wanted to know why. In Mesopotamia, over 4,000 years ago, Babylonian astronomers were already keeping detailed records of celestial events. This is a common historical fact. They built observatories, charted the movements of the moon and planets, and noticed subtle changes in the brightness of certain stars. These early records didn't include technical explanations. There was no mention of atmospheric refraction or turbulent air. but they did describe the visual experience of the night sky in remarkable detail. When a star flickered erratically or changed color, it was noted. Sometimes it was interpreted as an omen, but sometimes it was just another puzzle piece. The Babylonians weren't alone. Ancient Egyptians aligned their pyramids and temples with the stars, particularly Sirius, whose rising signaled the annual flooding of the Nile. They may not have written about the twinkling itself, but they knew which stars appeared most clearly and which were affected by the haze of the horizon, a subtle nod to the reality of atmospheric distortion. Then came the Greeks, who took things to a new level. The philosopher Anaxagoras, living around the 5th century BCE, was one of the first to suggest that stars were actually fiery stones far from Earth, a radical idea at the time. His student Democritus went even further, proposing that the Milky Way was made up of countless distant stars, too far to be seen clearly as individuals. These ideas weren't accepted by everyone. Some were downright scandalous, but they planted seeds of thought that would eventually grow into real astronomy. Fast forward a few centuries to Claudius Ptolemy, one of the most influential astronomers of the ancient world, living in Roman Egypt during the 2nd century CE. Ptolemy compiled a vast work called the Almagest, which included detailed star catalogs, planetary models, and observational techniques. He noted how stars near the horizon flickered more than those directly overhead, and how some stars seemed to flash different colors. He couldn't explain it. No one yet understood light refraction, but he recorded it, and that mattered. Ptolemy's observations were based on thousands of hours spent staring at the night sky, likely with nothing more than the naked eye and some very basic instruments. No lenses, no glass, just careful attention, and a lot of patience. And it wasn't just Europe. In the Islamic Golden Age between the 8th and 14th centuries, astronomers across the Middle East and North Africa made enormous contributions to our understanding of the stars. They built observatories in cities like Baghdad, Cairo, and Samarkand. They translated and preserved ancient Greek texts, added their own observations, and refined the accuracy of star catalogs. One of the most brilliant minds of this era was Abd al-Rahman al-Sufi, a Persian astronomer who compiled the Book of Fixed Stars in the 10th century. He made corrections to Ptolemy's data and added his own observations. He also described the color and brightness of stars in great detail, paying attention to changes over time that may have included descriptions of atmospheric effects like twinkling. And then there was Ulugh Beg, a 15th century ruler and astronomer who built one of the largest astronomical observatories of the medieval world in what is now Uzbekistan. His team created a star catalog that rivaled anything Europe would produce for another 100 years. Again, no telescopes, just the human eye sharpened by discipline and an insatiable curiosity. Twinkling wasn't just a poetic flourish for these astronomers. It was a real obstacle. When stars flickered or shimmered, it made it harder to measure their position or brightness accurately. So, they developed methods to minimize error. Observations were repeated many times over, usually from high elevations, where the air was thinner and less turbulent. Some even constructed narrow slits or sighting tubes to reduce the amount of atmosphere the light had to pass through before reaching the eye. Simple solutions, but effective ones. By the time of the Renaissance, European astronomers began to build on this legacy. Tycho Brahe, the brilliant Danish nobleman of the late 16th century, created the most accurate star charts ever made without a telescope. He noticed the twinkling of stars too, and he hated it. It interfered with his ability to record precise measurements. So he built massive instruments, giant protractors and sextants, to help him refine his observations. He even created a kind of proto-observatory on the island of Hven, where conditions were especially good for watching the stars. And then came Galileo. In 1609, Galileo Galilei pointed a telescope skyward and changed everything. Through the lens of his handmade instrument, he saw craters on the moons orbiting Jupiter, and most importantly, for our topic, He noticed that stars still twinkled through the telescope, but planets did not. The telescope magnified the tiny disks of planets, confirming what careful observers had already suspected, that twinkling wasn't a property of the object itself, but something happening in the space between. Galileo's findings helped establish that stars are incredibly distant, while planets are much closer. It was a turning point in how we understood the universe, and twinkling played a small but meaningful role in that realization. This brings us to a quirky detail that shows how far we've come. While we can now perfectly explain the science, the human experience of twinkling still holds a mysterious power. It is a fact that even today many of us will find a twinkling star more emotionally compelling than a steady one. The flicker feels alive, like a greeting. It adds a touch of magic that the perfection of science sometimes takes away. And so, while we have the tools to correct for the atmosphere, we still tell stories about the stars that flicker for us. And this leads to an interesting academic debate that continues to this day. Historians still debate whether ancient astronomers truly understood twinkling as an atmospheric phenomenon, or if they simply viewed it as an error or abnormality in their data. The evidence suggests they were well aware of its effects, but the philosophical implications of living in a universe where the light from a divine being or an ancestor could be distorted by the air they breathe was likely a difficult concept to reconcile with their worldviews. The question remains, at what point did the simple observation of twinkling stop being an omen and start being a puzzle of physics? Today, of course, we have technology that ancient astronomers could only dream of. We've launched telescopes into space above the twinkling atmosphere altogether. We've developed adaptive optic systems that adjust for atmospheric distortion in real time, allowing ground-based telescopes to de-twinkle the stars, if you will. We can now see stars not as shimmering points, but as stable sources of light, their secrets clearer than ever before. But it's humbling to remember that the foundation of all this began with the naked eye, with someone sitting under the stars, night after night, squinting at the flickering lights and wondering what it all meant. The twinkling may have frustrated them at times, but it also inspired them. It made the sky feel alive, just mysterious enough to chase. So the next time you find yourself looking up and watching a star shimmer, think of all the eyes that have done the same, from Babylon to Baghdad, from ancient Greece to Renaissance Europe. Each generation of sky watchers added a little more to the story, a little more knowledge, a little more awe, and maybe a little more appreciation for the beautiful imperfection of a twinkling star. So far, we've talked a lot about how stars twinkle, what causes it, and the stories we've told because of it. But now let's step into the present. Let's talk about how modern science handles twinkling stars, especially when twinkling gets in the way. Because as beautiful and poetic as it may be, twinkling is also a bit of a nuisance when you're trying to do serious astronomy. Astronomers don't exactly enjoy squinting at a flickering light show when they're trying to measure a star's exact brightness or track an exoplanet passing in front of its sun. It's like trying to read a book while someone keeps jiggling the pages. So what does science do when nature throws a glittery atmospheric curveball? It gets clever. First, let's revisit the problem. Earth's atmosphere is constantly shifting. It has layers of different temperatures, densities, and moisture levels all moving around, thanks to winds, thermal currents, and weather patterns. As starlight passes through these layers, it bends or refracts in unpredictable ways. This bending causes the star's image to jump slightly, changing its brightness and even color from one moment to the next. That's the twinkle. For casual observers, anyone lying on their back and looking up at the stars, it's charming. But for astronomers trying to capture a razor-sharp image or measure the precise light curve of a distant galaxy, it's a major obstacle. One solution is surprisingly simple: go somewhere high. The higher up you go, the less atmosphere you have above you. That means less turbulence, less distortion, and less twinkle. That's why some of the world's best observatories are perched atop mountains. Mount Mauna Kea in Hawaii, the Atacama Desert in Chile, or the Canary Islands in Spain. Up there, the air is thin, dry, and often incredibly stable. All of that helps astronomers get clearer views. But even at high altitudes, the atmosphere still moves. And so technology comes to the rescue. Enter adaptive optics, a clever system that allows telescopes to compensate for the distortions caused by the atmosphere in real time. Think of it like noise-canceling headphones, but for starlight. A common historical fact is that the idea for adaptive optics was first proposed in 1953 by astronomer Horace Babcock, but it took decades for the technology to catch up. He envisioned a flexible mirror that could warp and flex to counteract atmospheric blurring, but the mirrors and computers of the time simply weren't fast or precise enough. It wasn't until the 1990s, with the advent of faster computers and more advanced materials, that adaptive optics truly became a game changer for ground-based astronomy. Here's how it works. Telescopes equipped with adaptive optics use a flexible mirror one that can subtly change shape dozens or even hundreds of times per second. A powerful laser is shot into the sky to create a kind of artificial star, a reference point. Sensors detect how the atmosphere is distorting the light coming from this fake star, and then computers calculate the necessary adjustments. The mirror responds instantly, bending and flexing to cancel out the distortion. The result? A sharper image, a steady star, no twinkle. It's a marvel of engineering and computation, and it's allowed ground-based telescopes to achieve clarity once thought impossible without going to space. But of course, sometimes the best way to avoid the atmosphere altogether is to leave it behind. That's exactly what astronomers did in 1990 when they launched the Hubble Space Telescope. Floating more than 300 miles above Earth's surface, Hubble operates in the vacuum of space. No atmosphere, no distortion, no twinkling, just pure undisturbed starlight. The images Hubble captured changed astronomy forever. Swirling galaxies, glowing nebulae, and the faintest light from the farthest corners of the universe came into focus with breathtaking detail. And one of the quiet miracles behind all that beauty, no atmospheric interference. Hubble showed us what the universe really looks like when we strip away Earth's blurry filter, and it was dazzling. Since then, we've sent up other space telescopes, like the Kepler Space Telescope, which hunted for exoplanets by detecting tiny changes in starlight as planets passed in front of their stars. Such work would have been nearly impossible from the ground where twinkling could mask those delicate light dips. And of course, there's the James Webb Space Telescope, a successor to Hubble launched, with the goal of peering even deeper into space and time. It uses advanced infrared sensors and lives far beyond Earth's atmosphere, orbiting at a stable point in space known as Lagrange Point 2. From its vantage point, stars don't twinkle at all. They shine like the steady beacons they are. This leads us to a fascinating academic debate. Astronomers are still debating what is the best system to mitigate twinkling and related atmospheric issues. While space telescopes provide perfect clarity, they are incredibly expensive to launch and maintain. Ground-based telescopes are much more affordable and can be upgraded more easily. The debate isn't about which is better, but about how to best combine the two, using space telescopes for certain high-precision tasks and ground-based telescopes equipped with adaptive optics to handle a vast majority of the astronomical work. It's a question of both science and economics. But not all astronomy needs to be done from mountaintops or outer space. Even here on Earth, we can reduce the effects of twinkling through clever techniques. For example, by taking many short exposure photographs instead of one long one, astronomers can essentially freeze the motion of the atmosphere. This process, called lucky imaging, works on the idea that some of those images will catch a brief moment when the air is unusually still. Those sharp frames can then be combined into a clearer picture. There are also image processing algorithms that can help clean up twinkling effects after the fact. Computers are remarkably good at spotting patterns in noisy data, so even if the stars are flickering in real-life software, can help recreate what they would look like if the atmosphere weren't getting in the way. And let's not forget about radio astronomy, which deals with radio waves rather than visible light. Radio waves are much less affected by the atmosphere, so telescopes like the Very Large Array in New Mexico or the massive dish in China's Vast Observatory can observe the universe without worrying about twinkling at all. It's a different kind of astronomy, but one that complements what we learn from visible light. A quirky detail you might find interesting is that some of the first experiments with adaptive optics were done by the military. They were interested in using lasers to track objects in the atmosphere and needed a way to correct for atmospheric distortion. The technology was a classified secret for many years before it was declassified and adapted for use in astronomy, opening a whole new window to the cosmos. Still, there's something lovely about the fact that all of this effort, thousands of scientists, billions of dollars, decades of development, is aimed at seeing the stars as they truly are, all because of a simple twinkling illusion caused by the air above our heads. In a way, twinkling reminds us of our perspective. It's not the stars that are changing, it's us, or rather the thin layer of life-sustaining air we live in. We're the ones inside the snow globe. The stars are just shining steadily, unaffected, patient. That's part of what makes astronomy so magical. It's not just about looking outward. It's about understanding where we are in the grand scheme of things. We watch the sky not only to learn about distant galaxies, but to better understand the air we breathe, the ground we stand on, and the nature of our own perception. So the next time you see a star twinkle, you'll know exactly what's happening. You'll understand the physics, the history, the technology, but maybe, just maybe, you'll also smile at the fact that something so small, just a shimmer in the sky, can lead us to launch telescopes into orbit, build mirror systems that move faster than thought and reach deeper into space than we ever dreamed. That's a lot of ambition, all thanks to a little bit of twinkle. Let's take a moment to shift our gaze not just outward toward the stars, but inward toward ourselves. Because while science gives us all the tools to explain why stars twinkle, there's another part of the story that's just as important: how we experience it. The psychology of stargazing. There's something timeless about looking up at the night sky. It's a habit so ancient, so universally human, that it almost feels wired into us. Long before city smartphones or electric light, there were people lying on their backs watching the stars shimmer overhead. And remarkably, despite all that has changed, the feeling of awe that comes from stargazing hasn't faded one bit. It's calming. It's quiet. It slows you down in a world that seems to run on fast forward. But why does it feel that way? What's actually happening in your mind and body when you lie back, look up, and let the stars wash over you? Let's start with something simple, but powerful: awe. Psychological studies have shown that experiencing awe, whether from looking at a vast landscape, a towering mountain, or yes, the night sky, has measurable effects on your brain. It can lower activity in the parts of your brain associated with self-focus and ego. In other words, when you feel awe, you feel smaller. And strangely, that makes people happier. Why? Because it helps put your worries in perspective. That awkward email you sent this morning, that looming deadline under a sky filled with ancient starlight, those things tend to shrink a little. Not because they don't matter, but because they're just one tiny part of a much bigger picture. The stars remind us that we're not the center of the universe, and somehow that feels like a relief. And then there's the effect on your nervous system. Stargazing often happens in quiet, dark environments, places where you're naturally more relaxed. When you're outside at night breathing in cool air and focusing on something far away, your body begins to shift into what's known as the parasympathetic state. That's the rest and digest mode. Your heart rate slows, your muscles relax, your blood pressure drops. It's the opposite of the fight or flight stress response. In short, stargazing can make your body physically calmer. Even your eyes play a part. When you look at something distant like stars, Your eyes shift away from the close focus mode they use during screen time. That helps reduce eye strain and mental fatigue. It's like a reset button for your senses. And if you're lying on your back while stargazing, even better. Your posture naturally opens up your chest and encourages deep, even breathing. Of course, stargazing also does something to your thoughts. There's something about watching stars twinkle something quiet and rhythmic that invites daydreaming or night dreaming, really. Your thoughts start to slow down, unspool, and wander. You're not solving problems or making lists. You're just floating, drifting gently between wonder and calm. In fact, some researchers believe that stargazing can function a bit like mindfulness meditation. You're focusing your attention not on your breath or your body, but on something vast and beautiful. You become present without trying. And unlike meditation, stargazing doesn't require any special practice. You don't need training or discipline. You just need a sky. This mental stillness has real psychological benefits. Studies have found that regular exposure to nature, especially night skies, can reduce symptoms of anxiety and depression. It helps with emotional regulation, improves sleep, and enhances feelings of connectedness to others, to the world, and even to the universe. And speaking of sleep, there's good news there too. Stargazing can help reset your circadian rhythm. When you spend time under natural nightlight instead of artificial indoor light, your body starts to release melatonin at the right time. That's the hormone that helps you feel sleepy. So watching the stars doesn't just feel relaxing. It can literally prepare your body for rest, which makes twinkling stars the perfect bedtime companions. A common historical fact is that humans have always looked to the stars for guidance and comfort. Before clocks, the constellations told us the time of year. Before GPS, the North Star guided us across oceans. This deep practical connection has given way to a more spiritual and psychological one. The act of looking up, of feeling small in a vast universe, is wired into our brains as a universal coping mechanism, a way to put our worries into perspective. The stars, it seems, have always been a source of peace. Now let's add a little humor to all this science, because if there's one thing that's both deeply cosmic and delightfully silly, it's the fact that some of us will stare at the stars and think profound thoughts about time and space, while others will say, "That one looks like a potato," or "I think I saw a UFO." And that's okay. The sky is generous. It meets you wherever you are, whether you're contemplating your place in the cosmos or just enjoying the sparkle. The stars twinkle all the same. It's also worth noting that stargazing is a wonderfully low-pressure activity. There's no right or wrong way to do it. You don't need to know the names of the constellations. You don't need a telescope or a star chart or an app. You can just look up. That's it. And even if you're in a place with light pollution and you can only see a handful of stars, those few points of light can still work their quiet magic. Sometimes, less is more. One lonely twinkling star is enough to start a whole train of thought, one that takes you far beyond where you are. And finally, there's something deeply connective about stargazing. You may be alone in your backyard or on a balcony or curled up on a rooftop, but you're never really alone. Somewhere else in the world, someone else is probably doing the same thing, watching the same stars, seeing the same twinkle. They might be halfway around the globe or just a few towns away, but they're part of the same silent conversation. It's one of the few experiences that feels both personal and universal. The stars belong to all of us, and yet each twinkle feels like a private moment, a secret flicker of beauty meant just for you. A quirky detail that ties into this is that astronomers have found that people who live in rural areas with access to dark skies report feeling a greater sense of well-being and a deeper connection to nature. This isn't just because of the stars, but the entire experience of being under a truly dark sky. The absence of light pollution, the silence, the sheer number of stars visible, it all works together to create a profoundly meditative state that is becoming increasingly rare in our urbanized world. This leads to a fascinating academic debate that is ongoing in the fields of ecopsychology and public health. researchers are still debating the precise neurological and psychological mechanisms by which exposure to natural environments, particularly dark skies, influences human well-being. Is it a return to an evolutionary past? Is it simply a break from technology? Or is it something more profound, a direct connection to the cosmos that our brains are wired to find peace? In the question of how and why the sky makes us feel this way is one of the most beautiful and complex mysteries left to explore. So the next time you feel overwhelmed or restless, or just too full of thoughts, try looking up. Find a star, any star, and let your eyes rest on it. Watch it shimmer gently and unpredictably. Let your breath slow. Let your mind quiet. Let yourself feel small and vast and safe all at the same time. Because in that moment, you're not just stargazing. You're syncing up with something ancient, something bigger than your to-do list, bigger than your stress, bigger than anything happening on Earth. You're participating in one of the oldest, simplest, and most soothing rituals we know. And all it takes is a single twinkle. Let's imagine something rather beautiful for a moment. Somewhere out there, unimaginably far from Earth, a star is burning. It is steady, relentless, and ancient. It may be older than our planet, older than our sun, older than the very concept of time as we understand it. And from that star, a single particle of light, a photon, is released. It begins a journey, not just any journey, but one that will span vast cosmic distances and billions of years. Also, it can one day flicker in your eye for the briefest of moments. That's the story we're following now, the life of a photon from star to sky to you. Photons are tiny packets of light. They have no mass, they travel at the speed of light, and once they're set in motion, they don't slow down, veer off course, or get tired. They are the ultimate long-distance travelers, and they begin their journey deep inside the roaring heart of a star. Take a star like our sun, for instance. Deep within its core, nuclear fusion is constantly turning hydrogen into helium, releasing enormous amounts of energy in the process. Some of that energy becomes heat, some becomes radiation, and some becomes photons, little messengers of light that have to fight their way to the surface. And when I say fight, I mean really fight. A photon born in the core of a star might bounce around inside that star for tens of thousands, even hundreds of thousands of years. It doesn't move in a straight line. Instead, it gets absorbed and re-emitted by atoms over and over again, zigzagging like a moth at a disco until it finally escapes the star's surface and breaks free into space. Once free, the photon begins what might be the smoothest part of its journey, coasting through the near-perfect vacuum of space. Out here, there's very little to get in the way. No atmosphere, no clouds, no turbulence, just emptiness, darkness, and the occasional planet or dust cloud. A photon can travel for millions, even billions of years without colliding with a single thing. That means the light you're seeing from some stars tonight began its voyage long before the first humans walked the Earth. Let's pause on that for a moment. This is a common historical fact that is still a marvel to contemplate. If you're looking at a star that's, say, 100 light years away, the light from that star began its journey around the year 1925. Back when people were still driving Model T Fords and jazz was just hitting its stride, that photon was already en route. And now tonight, it finally arrives only to get knocked around in our atmosphere and made to twinkle. It's a dramatic finish for a very patient traveler. Now space isn't completely empty. Along its path, a photon might pass through clouds of cosmic dust, magnetic fields, or gravitational distortions caused by massive objects like black holes or galaxies. These encounters can bend the photon's path, slow it slightly, or scatter it, but for the most part, space is generous and lets light pass freely. Some photons do get diverted or absorbed, of course. That's why not all starlight reaches us. Some never make it past distant gas clouds. Others are captured by planets or swallowed by the void. But for the few that do find their way here, the final stretch of their journey is the most treacherous of all our atmosphere. We talked about how the atmosphere bends and distorts light in the last chapter. But let's look at it now from the photon's point of view. After sailing serenely through the vacuum of space, our photon now hits a swirling sea of molecules. It enters the atmosphere, and suddenly its graceful journey is over. It's like trying to run a straight line through a crowded room of dancing people. The photon gets jostled, nudged again, its path bending slightly. This way, then that. The result when it finally hits your eye is a little wobble in its apparent position, a twinkle. And speaking of hitting your eye, let's not gloss over how amazing that is. Your eye is made up of millions of light-sensitive cells, and in perfect darkness, it's sensitive enough to detect even a single photon. Yes, just one. This is a quirky detail that shows just how well-tuned our biology is. If your surroundings are dark enough and your eyes are fully adjusted, you might actually be seeing the impact of one lonely particle of light that's traveled across space for millennia, just to say hello. And when that happens, your brain interprets the signal as light from a star that to you has always been there, always twinkling. But really what you're seeing is a brief interaction between a particle and a person, a handshake across the cosmos. It's easy to forget sometimes that starlight is not just a glow in the distance. It's a physical thing. It's matterless, but not meaningless. Every flicker you see is a story, a fusion of survival of time and distance. It's like the star is whispering something to you, and the universe has bent over backward to deliver the message. In astronomy, there's a term for this kind of journey, the light path. It describes the route that photons take from a celestial object to our instruments or to our eyes. Understanding the light path is crucial because it helps astronomers determine how much of what they see is due to the object itself and how much is due to the distortions along the way. In a way, when you're looking at the stars, you're not seeing the present. You're looking into the past. The farther away a star is, the older its light is by the time it reaches you. That means the sky is a kind of living time machine. Every star is a snapshot of what it looked like years, decades, centuries, even eons ago. And yet we experience that light now in this moment. It's a curious paradox, light from the past, illuminating the present. This brings us to a fundamental academic debate in physics. What is the nature of the photon itself? We have just talked about it as a particle, a tiny packet of light. But in the double-slit experiment, remember that one light behaves as a wave. Physicists still debate the true nature of the photon. Is it a particle? Is it a wave? Or is it something else entirely, a kind of quantum entity that exhibits properties of both depending on how it is observed? The question of wave-particle duality is a deep philosophical one that has been ongoing for over 100 years. There is no simple answer, just a deeper appreciation for the mystery of what light, the very thing that connects us to the cosmos, truly is. You lying there gazing at the stars are participating in an ancient ritual. People have done this for tens of thousands of years, long before the science of photons or the word twinkle ever existed. And while the language and understanding may have changed, the feeling hasn't. The awe, the stillness, the sense of wonder, they've stayed the same. So the next time you spot a twinkling star, pause for a second and consider what you're really seeing. You're witnessing a photon's final destination. After a lifetime spent racing across space, dodging dust and gravity, it ends its journey not in a telescope, not in a lab, but in your eye. It's a gentle reminder that the universe is vast, ancient, and wild, but it's also personal. You're not just an observer, you're part of the story. You lying there with your thoughts are the final chapter in a photon's cosmic journey. And if that doesn't make you feel both tiny and cherished, I don't know what will. So far, we've looked at twinkling stars from our earthly perspective through the lens of science, myth, and even the calming effects on the human mind. But what if we changed the view? What if we left Earth behind and took our stargazing somewhere else? Would stars still twinkle on Mars or the Moon or from the deck of a spacecraft floating somewhere in deep space? To answer that, we need to remember exactly what causes the twinkle in the first place. Stars twinkle because their light passes through Earth's atmosphere, which is full of swirling air layers, temperature gradients, and varying densities. These invisible changes bend the light, causing it to dance and shimmer before it reaches our eyes. Remove the atmosphere and the twinkle disappears. So if you were standing on the moon, where there is no real atmosphere to speak of, what would you see? The answer is stars that don't twinkle at all. From the lunar surface, the sky is pitch black even during the day with no atmospheric scattering of sunlight, and the stars shine steadily and silently, completely unaffected by turbulence or distortion. They don't flicker or shift color. They simply glow. This is true not only for the moon, but for any airless celestial body, Mercury, most asteroids, even many of Jupiter's moons. Anywhere there's no atmosphere, stars appear exactly as they are, fixed, unwavering, and still. Now let's take a short hop to Mars. Mars does have an atmosphere, though it's much thinner than Earth's, about 1% as dense. It's mostly made of carbon dioxide, and it's far less turbulent than our own atmospheric soup. So, would stars twinkle on Mars? Sort of. The thin Martian atmosphere can cause a tiny bit of twinkling, especially when looking near the horizon, where the light has to pass through more air. But the effect would be far less dramatic than what we see from Earth. Most stars would appear steady to the naked eye, with perhaps the occasional gentle flicker. You'd have to watch very closely to notice it. In fact, early simulations by scientists suggest that if you were standing on Mars during a calm night, the stars would seem surprisingly stable. It would be like stargazing from a high mountain on Earth, but even clearer. Less flicker, less distortion, just stars shining with their ancient light, more quietly than we've ever seen them. And what about planets on Mars? Well, just like here on Earth, planets wouldn't twinkle much, but the effect would be even more muted than on Earth. Planets would look especially calm and steady against the Martian sky. A common historical fact is that the clarity of the stars from space was one of the first things astronauts reported. Astronauts aboard the International Space Station, for example, see the stars as sharp and unwavering. No twinkle, no shimmer, just dots of light perfectly still. Like sequins stitched into a cosmic quilt. The ability to observe the universe without the atmosphere's interference was a key scientific goal of the space age, and the early observations from orbit confirmed that twinkling was indeed a purely atmospheric phenomenon. Of course, this also means they don't get to enjoy that familiar poetic sparkle. The twinkle is something uniquely earthly, a side effect of our own atmosphere, a product of our particular way of being situated in the universe. It's something we share with all life that's ever lived here. In a sense, twinkling isn't a universal feature of the stars. It's a feature of our point of view. The stars themselves are indifferent to whether we see them shimmer. They shine as they always have, sending out light in every direction. But we, perched here on a planet wrapped in moving air, add our own subtle signature to the view. But now let's wander even further beyond our solar system, to a distant exoplanet orbiting a star far away. What would the night sky look like there? Well, it depends entirely on that planet's atmosphere. If it has a thick, turbulent atmosphere like Earth's, our light would twinkle just the same. If the air is dense but calm, like perhaps on a gas giant moon, you might get minimal shimmer. And if the planet has no atmosphere at all, the stars would again appear perfectly steady. This leads us to an active academic debate. Astronomers are still debating the precise composition and fluid dynamics of exoplanet atmospheres. We can look for signs of gases and water, but understanding how turbulent an alien atmosphere is and how that turbulence might affect our future observations from the surface of those worlds is a brand new field of inquiry. It's one of those quiet questions scientists love to ask. What would starlight feel like on an alien world? What stories would another species tell about the sky? Would they even have a word for twinkling? A quirky detail that ties into this speculation is that some researchers have even tried to simulate What the color of alien skies might be based on the composition of exoplanet atmospheres. Imagine a planet with a sky tinted green or deep red or golden orange. The scattering of light would change, and so might the character of the twinkle, how quickly it flickers. What colors shimmer most? How distorted the light becomes. In some hypothetical atmospheres, the twinkling might be more intense than anything we've ever seen. In others, it might be completely absent. The idea that somewhere on another world, a curious observer might look up and see the stars shine in perfect stillness. Well, that's both beautiful and a little eerie, because twinkling, for all its scientific causes, feels like something deeply human. It's part of how we recognize the night sky, part of how we connect to the stars emotionally, not just intellectually. It adds a softness, a rhythm, a kind of gentle heartbeat to the heavens. So yes, stars can twinkle elsewhere, but only if the conditions are just right, and on most worlds, they probably don't. They shine as they always have, but the dance, the glittering, flickering, ever so slightly mischievous dance, is a performance reserved for our stage. It's a reminder that the universe doesn't always need to be altered to be appreciated. Sometimes the magic comes from the lens through which we see it. So the next time you lie beneath a starry sky and watch those tiny lights twinkle, know that you're witnessing something rare. Not because the stars are unusual, but because you are. Because this planet, this atmosphere, this particular swirl of air and light and perspective is giving you a show that few others in the cosmos might ever see. Twinkling, it turns out, is one of Earth's greatest special effects, and we get front row seats. And so here we are at the end of our journey through the night sky. We've unraveled the science behind that gentle shimmer, explored the layers of air that dance above us, followed photons across the universe, and wandered into ancient myths and faraway planets, all of it sparked by a single simple question. Why do stars twinkle? We've seen how the answer is both beautifully straightforward and endlessly complex. It's the atmosphere, yes, but also the history, the perspective, the emotion, and the imagination that we bring to the stars when we look up. The twinkle is caused by shifting air, but the meaning we find in it, that's entirely human. Somewhere tonight, light from a distant star is just now reaching Earth, filtered through our unique little pocket of sky, flickering gently as it lands in your eye. And maybe that tiny glimmer brings with it a little sense of peace, a little quiet, a moment of wonder, something to hold on to even as the rest of the world moves on. Let's pause and reflect on all we've learned. We began with a simple observation, the flicker of a star, and we followed it all the way from the chaotic heart of a sun to the quiet stillness of your own mind. We've seen that the ancient stories our ancestors told were not wrong. They were just a different way of understanding the same mystery. This is a common historical fact, that every culture finds a way to tell stories about the stars. And we've seen how the steady, unwavering glow of a planet reminds us that the stars themselves are perfect, and it is only our earthly position that makes them dance. We also learned that all of our incredible modern technology, from adaptive optics to space telescopes, is dedicated to removing that poetic shimmer, to seeing the universe as it truly is. This is a testament to the human desire for knowledge and accuracy, but it's also a testament to our profound connection to the sky. There's a charming and gentle, quirky detail that shows this connection. Some of the most beautiful and scientifically valuable images of the night sky have been captured by amateur astronomers using simple techniques like lucky imaging, where they take thousands of quick photos to find the one rare moment of atmospheric stillness. These are not professional scientists with billion-dollar telescopes, but curious individuals with a passion for the cosmos, showing that even with all of our technology, the simple act of looking up with a patient eye is still a powerful tool for discovery. And yet, despite all we've learned, some common misconceptions about the cosmos can creep in. So let's gently clear the air around them. There's a myth that our goal in astronomy is to conquer or tame space. But this is not the case. The universe, is far too vast and indifferent for us to ever hope to control it. The goal of astronomy is not conquest, but understanding. It is an act of humility, a way to see our place in the cosmos, not to dominate it. It's a pursuit driven by awe, not ambition. Another myth is that our scientific understanding of the universe ruins the magic. People sometimes fear that if they know why stars twinkle, they will no longer be able to make a wish upon them. But this is a beautiful misunderstanding. Knowing the science of the twinkle doesn't take away the poetry. It adds to it. It tells us that the universe is not just mysterious. It is intelligent. Its laws are elegant. Its functions are beautiful. And its grandeur is beyond our wildest imagination. A wish on a star is not less magical because it is sent upon a particle of light that has traveled millions of years only to be made to dance by the air above our heads. If anything, it makes it more magical. It tells us that our desires are carried by the universe itself from the heart of a star to the quiet of our own minds. There is a final academic debate that ties all of this together. Philosophers and cosmologists still debate what the human role in the universe truly is. Are we just accidental observers, a random byproduct of cosmic evolution? Or is our consciousness our ability to tell stories and feel awe a fundamental part of the universe itself, a way for the cosmos to know itself? The answer, of course, is a mystery and a beautiful one. But as you lie here resting, you can feel that perhaps it is both. You are a product of the stars, and your wonder is a reflection of their light. So before you drift off, let me ask again, where in the world are you watching from? What time is it where you are right now? Are you tucked in, just settling down, or maybe already floating somewhere between thoughts and dreams? Wherever you are, I hope this journey has helped bring a little calm, a little clarity, and a little curiosity to your evening. And if you've enjoyed our starlit stroll, I'd be honored if you left a like, maybe subscribed, or shared where you're watching from in the comments below. After all, the sky belongs to all of us, and even though the stars shine for everyone, the twinkle, that little wink from the cosmos, is just for you. Now let the light from the stars, both real and imagined, wash over you. There is no longer any need to hold on to these ideas. You can let them go like a whisper on the wind. The atmosphere will continue to dance, the stars will continue to shine, and you, a small, beautiful part of this great universe, are right where you need to be. Feel the cool air on your skin. Listen to the quiet in the room. Let the worries of the day drift away like clouds. You are safe, you are at peace, and the night sky is here to guide you. Just breathe. Let your thoughts soften and your eyelids grow heavy. The journey is over, but the dreams have just begun.